In the first second of the universe, every rule was written. Every force, every particle, every atom that would ever exist. And matter, the stuff you're made of, nearly didn't make it. Its survival came down to a 1 in a billion accident. That accident happened before the universe was 1 microsecond old. We didn't always know the universe had a beginning. For most of scientific history, the universe was assumed to be eternal and unchanging. That changed in 1929, when astronomer Edwin Hubble discovered something remarkable. Galaxies were moving away from us. And the further away they were, the faster they moved. If the universe is expanding today, it must have been smaller yesterday, and smaller before that, and smaller still. Run it backward far enough, and everything converges. A Belgian physicist named Georges Lemaitre had proposed exactly this in 1927. He called it the primeval atom, the universe beginning as a single, compressed point. A British astronomer named Fred Hoyle thought this was absurd. In a 1949 BBC broadcast, he mocked the idea, calling it the Big Bang. The name is stuck. But the Big Bang was nothing like an explosion. There was no central point, no pre-existing space for matter to fly into. Space itself was born. That starting point wasn't a location. It was a moment in time. A moment that all of space shared simultaneously. At the very first instant, all 4 forces of nature were fused into one. Gravity, electromagnetism, and both nuclear forces. A single unified force. The temperature was roughly 100 million trillion degrees. And our physics breaks down completely at this scale. Einstein's theory of gravity and the rules governing tiny particles contradict each other here. Scientists haven't solved that contradiction yet. The universe begins in a zone we genuinely cannot describe. Then, almost immediately, gravity separates from the rest. The other 3 forces stay unified. For now, a fraction of a second later, something extraordinary happened. The universe inflated. Not just expanded. Inflated. Exponentially. An energy field that filled all of space was sitting in an unstable high-energy state. Like a ball balanced on top of a hill, ready to roll. When it rolled down, the stored energy drove explosive expansion. A region smaller than a proton grew to something larger than a grapefruit. In a window of time, too short to even have a useful comparison. This solved 3 deep problems at once. Why does the entire sky have the same temperature everywhere you look? Even in regions that could never have communicated with each other. Because before inflation, they were all the same tiny patch. Why is the universe's geometry so precisely flat? Because inflation ironed out any curvature. But the most astonishing consequence was something else. That energy field had tiny random fluctuations. Fuzziness in its value from place to place. Inflation stretched those fluctuations from subatomic to cosmic scales. Those density variations are the seeds of everything you can see in the night sky. The Milky Way. Your existence. Quantum. Noise. After inflation, the forces kept separating. The strong nuclear force broke away from the rest. Then, at 1 trillionth of a second after the Big Bang, something fundamental changed. An invisible field that fills all of space. The Higgs field switched on. Before this moment, every particle was massless and traveled at the speed of light. After this moment, particles began to interact with the Higgs field. That interaction is what we call mass. Without mass, atoms are impossible. Chemistry is impossible. Every time you step on a bathroom scale, you're measuring the Higgs field at work. The same field that switched on 1/1,000,000,000 of a second after the Big Bang. The two remaining forces, electromagnetism and the weak nuclear force, finally split apart. The universe now had 4 distinct forces, exactly as we know them today. For most of the first second, the universe was a hot soup. Quarks, the tiny particles that build protons and neutrons, existed freely, too hot and energetic to bind together. Scientists have actually recreated this in laboratories. Smash gold atoms together at near light speed in a particle accelerator, and you briefly get the same soup. The shock: it doesn't behave like a gas. It flows like a liquid. In fact, the most perfect liquid ever measured. Water is nearly 5,000 times more viscous than the early universe was. At 1 microsecond after the Big Bang, the universe cooled enough for that to end. Quarks became locked inside protons and neutrons. Isolated quarks would never exist again. Here's the problem. The laws of physics treat matter and antimatter nearly identically. The Big Bang should have produced exactly equal amounts of both. They should have annihilated completely, leaving a universe of pure light. No atoms, no stars, nothing. Instead, something tilted the balance. In 1967, physicist Andrei Sakharov identified 3 conditions that must all be met for matter to win. All 3 were met in the early universe. But here's the mystery. When physicists measure how differently matter and antimatter behave, the difference is too small, millions of times too small, to explain why we exist. We know matter won. We don't fully know why. For every billion matter-antimatter pairs that annihilated in a flash of light, 1 matter particle survived. Just 1. Those survivors became every star, every planet, every atom you've ever touched. We are the 1 in a billion. After quarks bound into protons, the universe was still dominated by electrons and neutrinos. Electrons and ghost-like particles, called neutrinos. At around 1 second after the Big Bang, neutrinos stopped interacting with ordinary matter. They decoupled, and from that moment, they streamed freely through the universe. They're passing through your body right now. The faint glow of radiation that fills our entire sky is the cosmic microwave background. It shows us the universe at 380,000 years. That's as far back as light can take us. Those relic neutrinos carry information from 1 second after the Big Bang. We haven't directly detected them, but their existence is confirmed through other observations. At 1 second after the Big Bang, the universe held a specific mix of protons and neutrons. About 1 neutron for every 7 protons. That ratio was set by everything that happened in the first second. Starting at about 3 minutes, protons and neutrons fused. The first atoms ever made, mostly hydrogen and helium. Scientists can calculate exactly what mix of elements should have formed from that ratio. Then compare it to what we observe in the oldest, chemically unchanged stars today. Helium, predicted at 25% of all matter by mass. Observed, 24 to 25%. Heavy hydrogen, predicted at roughly 1 in 40,000 hydrogen atoms. Observed. Exactly that. The match is one of the most precise agreements in all of science. A direct readout of events that happened 13.8 billion years ago. One anomaly remains. Lithium. The prediction is 3 times higher than what we observe in old stars. That mismatch is still unsolved. It may require new physics from the first second itself. Next time you look up at the night sky, you're looking at everything that survived the universe's first second. The experiments ran. The universe found a way. And so did you. The full story of how is still being written. There's more to discover. See you in the next one.